Does your space crew have issues crashing into asteroids? This sensor may be the one for you!
This special little sensor can accurately detect and follow asteroids within a range of 400 centimeters to give our scaled-down spaceship crew ample time to dodge the catastrophic asteroids.
The ultrasonic sensor measures distance by sending and receiving ultrasonic waves, timing their journey. The time it takes the wave to return is converted to distance. Using this ultrasonic technology to our advantage, we made it into a mini radar that can detect incoming asteroids and debris that our crew may face when entering unknown worlds.
The advantages of the ultrasonic sensor include 1. Contactless distant measurement, meaning the sensor doesn't have to touch the object being measured, like a ruler, in order to measure it. 2. They can detect any materials. 3. They have a greater range than other proximity sensors. However, the sensor is sensitive to temperature and cannot work in space due to sound not traveling in a vacuum. In addition, the shape of the object can affect accuracy. For best results, a plain wall is recommended.
The HC-SR04 Ultrasonic Ranging module consists of 2 ultrasonic transducers. One acts as a transmitter. The module receives an electrical signal, or a constant electrical signal in our case, and sends out an output sound wave through its output acoustic transducer. This is our trig pin in our code. The other acts as a receiver. This module will test if there's any sound signal returned through the input acoustic transducer and measures the time difference between the output signal and the input signal. This is called our echo pin. The time is then divided in half because we want the time it took to get to the object, not the total time, and then convert it to distance using the speed of sound. You can tell by the little T and R on the base plate of the sensor which side is which. Other common applications for ultrasonic transducers are ultrasounds, sonar, and sometimes they're also used in security systems when detecting breaches once the alarms are set. For our signal chain, it all starts with our voltage output. This then results in the output acoustic transducer sending out a sound wave. That sound wave is then deflected by an object and is received by the input acoustic transducer. The time between the output and input is then captured by our microcontroller, which then of course needs to be calibrated. The time is then converted using the speed of sound to give us a final measurement of distance.
This Arduino program uses an ESP32 board to control a servo motor and an ultrasonic sensor to scan and measure distances in a sweeping motion, similar to a basic radar system. It begins by including an ESP32 servo library, which allows the ESP32 to control a servo motor. This library was created and is maintained by Kevin Harrington, and it faithfully replicates the schematics of the Arduino servo library for use with the ESP32. The ultrasonic sensor's trigger and echo pins are assigned to digital pins 22 and 2, respectively. A few numerical variables are defined to store the duration of the ultrasonic pulse and the calculated distance. A servo object is created, and the speed of sound is defined as 0.034 centimeters per microsecond. In the setup function, the trigger pin is set as an output, the echo pin as an input, and the serial communication is initialized at 115,200 baud. The baud rate determines how fast data is sent over the serial connection, in this case, 115,200 bits per second, ensuring that the ESP32 can reliably communicate readings to the serial monitor. The servo is attached to pin 23. In the loop function, the servo rotates from 15 to 165 degrees and back, stopping at each degree to measure the distance using the ultrasonic sensor. At each step, the distance is calculated by sending a short pulse from the trigger pin, timing the return echo, and converting that duration into a distance using the speed of sound. The angle and corresponding distance are then printed to the serial monitor. This process continues indefinitely, creating a continuous scanning motion that outputs distance data. In our scale model, this output distance is in centimeters. This program is perfect for keeping astronauts safely out of asteroids' way without needing supervision or constant human input. The intended calibration process was to place the sensor at the end of a ruler, position a flat plate at a known distance along the ruler, and record both the known measurement and sensor's readings in Excel. From there, we plan to create a linear equation to determine the sensor's adjusted sensitivity and null offset, which would then be implemented in the code to correct future readings. However, the issue we ran into was inconsistency in the sensor's error. Sometimes it read 1 centimeter more than the actual value, other times 2 centimeters less. Given this unpredictable variation, we concluded that a deviation of 1 to 2 centimeters wasn't sufficient enough to prevent the cruise ship from meeting an unfortunate outcome. As a result, we decided not to modify the code based on this calibration.
Warning: the sensor is intended primarily for educational use and is not recommended for the extreme conditions encountered during space travel. Use in a vacuum will result in critical failure as sound cannot travel without a medium. Any harm caused by ignoring this warning is the responsibility of the user, and we are not liable for any misuse. Side effects of using ultrasonic sensor in space may include loss of data, inaccurate readings, delayed mission progress, unexplained floating, increased existential dread, and spontaneous reflection on why you didn't use LiDAR or optical alternatives instead. Always consult your aerospace engineer before selecting a sensor. Ultrasonic sensor is not recommended for use outside the stratosphere.